Good evening, everyone. Welcome to the eighth live session for the course Advanced Reinforced Concrete Design offered by NPTEL. I am Arshit Agrawal, a PMRF scholar from Department of Civil Engineering, IIT Bombay, and I will be conducting weekly session for the entire course duration of this course. So in today's session, we'll first have a very quick recap to week 7 content that we concluded last week, and then we'll move into the week 8 learnings. So week 8 recording were oriented. In today's session, we'll continue our discussion first towards what all things we left in the last session, that was based on understanding the flexure versus shear failure of reinforced concrete. So in this, we will discuss about understanding the concept of A by D ratio and Mohr circle. Then we'll see shear reinforcement design of an RC member based on IS 456 guidelines. After shear, we'll start discussing about torsion in reinforced concrete. What is torsion, how torsion cracking occurs, what is the science behind torsion, and how we estimate the maximum torsion stress based on soap film analogy and thin walled tube analogy. Okay, and finally, we'll see how torsional movement is incorporated in RC design as per IS 456. Okay, so today, along with quick theory recap of different segment, I will introduce you with several questions to challenge your understanding. And in total, we'll have around 18 questions that we'll discuss. Some numericals and some will be theoretical. So since we have a lot of content to discuss today, what I will do, I will keep the theory part a little bit quick, and I will expect that if you have any doubts or any problem in any of the segment of the theory, just keep it typed in the chat box, or whenever I am taking a pause for discussing question, just quickly unmute and speak so that we can complete the session in 2 hours, because from next session we'll start discussing about columns, and that is a very different discussion from whatever we had till now. So that's why I'm not keeping anything left for the next session. Okay. So last week we continued discussing about flexure behavior of reinforced concrete by discussing the flexure design as per IS 456 guidelines. We saw the assumptions that is made by IS code for flexure design, and we saw the strain distribution and the stress distribution for a RC member. Okay. Now, to go deep into understanding the stress block, we looked into individual stress strain profile of concrete and steel. For steel, we understood how we get the actual curve from actual curve, how we get the design curve by multiplying a factor of 1.15. And for concrete, we understood how different safety factors like zero point 0.8 for converting cube strength to cylinder strength, 0.85 for the size criteria to differentiate between the large scale concreting on field and small scale concreting that we do in laboratory, and 1.5 as additional safety factor to bring the that we additionally take as a safety factor, and these all they combine to bring the characteristic strength from FCK to 0.45 FCK. We saw multiple numerical questions to understand the application of different formula for design purpose, and then we saw design of doubly reinforced section as per IS 456. The design is approached in two steps. First step is we design a balanced RC section having a moment of resistance mu1, and then for the remaining moment m minus mu1, which we denoted as mu2, we design the steel in compression, and to balance the steel in compression, we provide steel in the tension side. So we saw a numerical just to understand the application of this approach. Then we saw design of flanged section, where we saw that the design has three subdivisions based on the depth of neutral axis x and the flange depth df. So if my depth of neutral axis is greater than the depth of flange, then neutral axis we say it lies below the flange part, so the entire compression block is in the flange. Okay, if the neutral axis depth is less than the depth of flange, then we say neutral axis lies in the flange part. So again we have two more cases, whether the flange is uniformly stressed or not, and that judgment we get from df by d ratio. If it is less than zero point 0.2, we say that the flange is uniformly stressed, and if it is more than zero point 0.2, we say flange is not uniformly stressed. So for each of these cases we saw how we estimate the moment of resistance, and then we solved a numerical just to see the approach, how we go along with the solving a problem for a flange section. Finally, we talked about shear behavior of concrete. We understood what is shear failure, how it appears as diagonal cracking, and how we estimate the shear stress of concrete, and saw how it varies with the distance from the neutral axis that you can see in the second diagram here. Okay. Okay, so this is how what we saw. Okay, for this we derived this shear stress equation. Tau is equal to vq upon it. Q is the area moment, v is the shear force, I is the moment of inertia, and t is the distance. This ib we can write. Okay, width of the member. Okay, so this was all we discussed in the last session. Now, if we go back to the last part of the discussion again, we know there are two theories. The Flexure theory, which says m upon ei is equal to 1 by r, and 1 by r is equal to epsilon upon y. So, this is Flexure theory. So, at a particular section, okay. If I want to calculate the shear flexure stress, so stress I can write it is equal to modulus of elasticity upon epsilon. So stress will be equal to my by I. Okay, from combining these two equations. Okay, now at a particular section, if I want to determine the maximum flexure stress, so I will take it at the end, this end section. Okay, so at the end y will be equal to d by 2, distance from the neutral axis, and I we know it is bd cube by 12. So we'll get the flexure stress as a constant c1 times m upon bd square. Okay, so this will be a general notation of how a flexure stress will be. Okay, similarly for the same section, if I determine the maximum shear stress, so we can write tau is equal to vq upon ib. Okay, at the center the shear stress will be maximum. So we saw this calculation last time, how we estimate the tau max value. It is 3v upon 2bd. So again, this is something which is constant and which will vary as we change the distance from the neutral axis. But this b upon v upon bd part, it is something that will remain constant in everything, in all the sections. So we can write tau is a function of c2 times b upon bd. So if we take this ratio of flexure upon shear stress, so we get it will be something a new constant c3, which will be like something c1 by c2 into m by v upon d. Okay, now if we take a simple free body diagram of a beam under loading, so we know that where is my cursor? We know that we can form the shear force diagram and bending moment diagram, and at any distance x from one of the support, we can write the equation of m is nothing but p into x, because here when we balance forces it will be p, so m will be nothing but p times x, and shear force will be v. So m by v ratio we can see it will be equal to x is the distance from the support. So if I replace this by x, or in general by any distance a, okay, so we know the flexure stress upon shear stress, it will be directly proportional to this a by d. Okay, now if we see how this a by d is important to us, so this ratio dictates which type of failure mode will dominate in a reinforced concrete section. So see, there are three cases right now that are in front of me, and all three have different a value. Okay, this is a smaller a value, this is a little more a value, and this is the highest a value. Okay, so if my a by d ratio is less than 2.5, this case I am talking about, when my load that is acting is very close to the support, so in such cases, what will happen? We will see that shear failure is dominating by creating a arch failure which is diagonally running from the support to the loading point. Okay, so from this point, directly a crack will run diagonally at an angle of 45 degree, and it will cause shear failures. Okay, so in such cases, when A by D ratio is less than 2.5, we say that shear failure dominates over flexure failure. Okay, now if my A by D ratio is more than 2.5 and less than zero point 0.5, so we say there can be both shear failure and flexure contribution. Both shear and flexure, they can contribute to the failure. Okay, there can be a shear diagonal failure, okay, like this. There can be cracking due to flexural stresses, which then propagates at shear crack later on. And then or else there can be cracking at the top, okay, due to compression, and which is clubbed with the shear failure to make a diagonal cracking. Okay, so there can be three types of failure: diagonal tension failure, shear tension failure, or shear compression failure. Since shear compression tension failure, what is happening here? In tension, the concrete is failing in flexure, and then shear is coming into picture. And in shear compression failure, the concrete is failing in the compression part in flexure due to flexure, and it is combined with the shear cracking. Okay, and if my A by D ratio is greater than 5, that means my load is very near to the middle part and very far away from the support. Then we say that flexure failure dominates, and we see mostly see a straight line cracking. Okay, so we saw example last time of a bridge deck, in which we saw there are incline cracking near the supports, and vertical cracking in the mid span. So this is the theory that is governing that cracking pattern. Okay, now the same thing is explained on this slide also. So you see, when my A by D ratio is less than 2, there is a kind of an arch action. So directly cracking is happening, which is crack is running from support to the loading point. However, if my A by D ratio is more than 2.5, then there can be shear tension failure and shear compression failure. Okay, so the failure, they start as a flexural crack in these cases and then propagate as a shear crack. Okay, so here the failure initiates like this and then propagates like a shear crack, and in this shear failure initiates like this and then propagate like a shear crack. Okay, now just based on this A by D ratio concept, try to answer these three simple questions just to see whether you have understood the concept or not. So the first question says, for a slender RC beam with the shear span to depth ratio of less than 2.5, which mode dominates in failure? So what will be the answer for this? Can any one of you tell me?
A. Shear compression.
A by D ratio is less than 2.5. So it means that the loading is acting very near to the support.
Uh, Arch failure.
Yeah, the correct answer will be arch failure. So we saw in the previous slide itself that when the load is acting very near to the support, the crack directly runs from the support to the point of loading. So it is like a diagonal crack which is forming. So since it is very near to the support, we say it is an arch failure that is happening. Okay, the shear span to depth ratio A by D primarily influences what? So what is the influence? What this A by D ratio is influencing? Can anyone tell me based on the options that I have given?
A.
Yeah, the correct answer is A, because as the A by D ratio changes, the type of cracking changes. If my A by D ratio is very small, we say that the shear cracking is happening. It is an inclined cracking happening. If my A by D ratio is very large, it means that the point of loading, it is very near to the middle part. Then we say it is the flexure failure which dominates, and we see a diagonal cracking that will happen. Okay. Question number three, which of the following statements is correct? So there are four statements. Try to read all the four statements and tell me which one is correct. Can anyone tell me the answer?
It is C, sir.
Yeah, the correct answer is C. So when the A by D ratio is small, it means that we are very close to the support. So that's why we say shear failure will occur before flexure failure. Okay, so in this way, this simple concept we can understand. Okay, so this concept is very simple of shear span to depth ratio, but it is also very important and it has a very strong practical implication. So when you will see some big beam and cracking pattern in those beams, so you will see clearly this distinction that we are discussing here. Okay, try to answer more questions. Okay, it's again based on the same theory of A by D ratio. Inclined cracks means the shear cracks. In RC beam, they generally initiate when they initiate. When we say shear cracking will happen in a reinforced concrete beam.
D.
Yes, the correct answer is B. So how they say? So typically, when we say shear crack, they initiate near the support where the shear force is high. Okay. Now this mechanism that principal tensile stress at web exceeds the tensile strength of concrete. So it is due to we will understand shortly what we mean by principal tensile stress. So when these stress they exceed the tensile strength of concrete, then we'll see that. So we know one basic theory: when the stress is more than the strength, then the cracking will happen. Now, what is the meaning of this principal tensile strength? Principal tensile strength basically means the maximum stress at a particular location. Okay, so why this cracking it happens diagonally, why it is not going straight from here, so that we'll see. So when we say at this point the crack, the principal direction is at the 45-degree angle at which the stresses are the maximum, and at this angle the stress they exceeds the strength of concrete, and that's why it runs diagonally from the support to the point of loading. So that's why we say principal tensile strength when it exceeds the principal tensile stress when it exceeds the tensile strength of concrete, the shear cracking happens. Okay, so this concept we'll shortly understand when we'll talk about Mohr circle. Okay, question number 5: the slope of inclined crack in beams without shear reinforcement, it will depend on. So suppose I have not provided the shear reinforcement. So the slope of the crack that happens, on what factor it will depend? Okay.
C, sir.
Yes, the correct answer is C. So when the slope, when the A by D ratio, the shear span means the A value, the point, the distance from the support where the load is acting. Okay, that is known as the shear span. Okay, so when this ratio is very high, we say that the crack is vertical, so slope is 90-degree. When this ratio is very small, then we say the crack is inclined, so slope is 45-degree. Okay, so after the first diagonal crack forms in the beam, okay, just try to complete this statement. What will happen after first diagonal crack forms in the beam? Suppose there is a small diagonal crack that has formed in the beam. Now, what will be the response of RC beam, a reinforced concrete beam, to that crack? What will resist the crack from growing further?
Stirrups and aggregate interlock.
Yeah, so we will see shortly different ways in which shear is resisted by a reinforced concrete system. So unlike flexure, where we say that there is only the reinforcement that we provide in the tension side which resists the bending, in shear both concrete and the additional steel reinforcements, shear reinforcement we provide both contribute in resisting shear crack. Okay, and how concrete resists shear crack? That is due to aggregate interlock, which resists the crack from propagating through it. Okay, so this theory will again shortly understand. Okay, any doubt in this concept of A by D ratio and how shear and flexure crack vary?
No, sir.
Okay, so now we'll move ahead uh, to talk about Mohr circle. So in one question, if you remember in the last slide, we saw a term was used principal stress, which if you go back to earlier discussion means the maximum and the minimum stress resulting from combination of two stresses. Okay, so principal stress can be maximum stress also and minimum stress also, which results from combination of multiple stresses acting at a location. Now, to calculate principal stress at a particular location, we use Mohr circle. Okay, how? So, in a reinforced concrete member which is subjected to a uniformly distributed load, suppose I take a small element dA. Okay, this is small element with a cross sectional area dA near the top. So, since this is near the top, this element will be under some flexure compression. Okay, that you can see is acting here. Okay, and it will be under some shear also, though we know that shear diminishes as we go from near till the top, but it is near the top, so it will have some shear also. Okay, now if we map these 2 points of combination of these 2 points on an xy plane where x-axis represents the flexure stress and y-axis represents the shear stress, so we will have these 2 points. Okay, this is one point, this is second point. Okay, we will give some notation to the sign convention. Suppose compression is positive, tension is negative, and in shear clockwise direction, suppose we say it is positive, anti-clockwise direction is negative, so we can map 2 points on the xy plane, and assuming these 2 points as a diameter, we draw a circle. Okay, so this circle that we draw, it is known as Mohr circle, and the point at which this circle interacts with the x-axis, these are known as the principal stresses. Okay, so this is the Mohr circle that I have drawn from these two known values, and then after drawing the circle, the axis, the point at which it crosses the principal x-axis is known as the principal stresses. Okay, so just going a little beyond what was there in the recorded session, suppose if I know this point A. Okay, we saw what is Mohr circle. Okay, now I know this point A and point B on the Mohr circle. Then shear and flexure stress at any point N. How I can determine that? Okay, we can determine by knowing the known, from the known points we can determine shear and flexure at any point on the circle. Okay, so we know at this point the shear stress, it is given by this equation. So this is a relationship that will that has been derived for Mohr circle. So shear at any point N, it is equal to half times sigma x minus sigma y times sine of 2 theta plus tau xy times cos of 2 theta. Okay, so this sigma x, sigma y, and tau xy, these are the value of shear and flexure that we already know. From this known value, and if we know at what angle we are rotating from our point, we can determine shear and flexure at any point. Okay, so this was for flexure, and similarly there is a formula for shear also that can be used. Now radius we can calculate as distance between these 2 points, so that is very simple, that calculation. And sigma average, if I know sigma 1 and sigma 2 principal stresses, then I can calculate sigma average also. So as we did for this nth point, if I know the critical angle by which I will rotate to get this point, then I can determine the sigma average also. And for knowing this angle 2 theta p, we use this formula. Okay, tan to theta p is equal to 2 times tau xy upon sigma x minus sigma y. Okay, so if you know only these 2 points, and if you want to estimate the principal stresses without drawing a Mohr circle, you can calculate the 2 theta p value using this formula. Once you know the 2 theta p value, you will get tau n and sigma n. Okay, tau n will be 0. So for this theta p, you will see tau n will come out to be 0, and sigma n, you will get two values. Okay, 2 theta p and 180 minus 2 theta p. If you will do, you will get two values of sigma 1 and sigma 2. From sigma 1 and sigma 2, you can calculate sigma average. Okay, so without drawing the Mohr circle, using these equations, we can easily calculate stress at any point. Okay, on the circle. Okay, now if we see how this Mohr circle will change based on the location in reinforced concrete beam. So I have here 4 points. Point number one is near the bottom, where there is no shear stress, just flexure tension. So this is point number one. Now if I go along the crack, the second point is somewhere a little above this, where there is both flexure tension and there is shear. Okay, then there is a point in the middle where there is just shear and there is no flexure, and then there is a point in the compression zone where there is flexure, compression, and shear. Okay, so for each of these, if we draw more circles, so for the first block, they where there is no flexure and no shear, so our Mohr circle will look like this. Okay, so I have these 2 points that has been known to me, and using these 2 points, I have drawn the circle. Okay, now for the second case where there is flexure tension and there is shear, so I will have 2 points like this, somewhere like this. Okay, and based on that shear value I know, so I can draw a Mohr circle again, and then I can estimate the principal stresses. Okay, again when there is only shear and there is no flexure. Okay, this was case number 3, sorry, this is case number 2. So there is 1 point here, 1 point here, which is known to me. From this I can draw a circle, and I can estimate the principal stresses. Okay, case number 3, where is only shear and no flexures. I have point one here, and second point is here, using which I have drawn the circle, and I can calculate the principal stresses. And in the fourth case, I have 1 point maybe here and here, or here and here, using which I have drawn a circle and I have estimated the principal stresses. Okay, so in this way, as we change the location of the member that we are studying, we will see that the calculation of the Mohr circle will also change, and this 2 theta p value that we are calculating, it will also change, which will dictate how the crack is propagating. Okay, so based on the formula of theta p that we saw earlier, we can from the trajectory of principal tension and principal compression force also, based on the moment of my element block, movement of my element block that I am looking at. Okay, so you can see here, so this figure, where is my cursor? This figure represents the principal stresses in a homogeneous isotropic beam, and this solid line, red one, it's showing the tensile force trajectory, how it is changing, and the blue dotted line, it shows the compression force trajectory, how it is changing. So based on this, we can estimate how the crack will grow. So here, the principal stress will propagate at this angle. As we'll go a little away from the support, we'll see that the crack will become inclined. So at this inclination, my principal stresses will lie, and crack will move along this side, and it will, as we go at the top, it will try to become horizontal. Okay, so this is the contour map, we can say, that we can form from Mohr circle if we take elements at different positions. Okay. Now, based on this Mohr circle concept, just try to answer these three simple questions. And in the meantime, if you have any doubt regarding the this concept, you can ask. I'll just check once if there is any question. Okay. So try to answer this question number 7. For a state of pure bending in a concrete beam where there is no shear, uh, how Mohr circle will look like? So can anyone tell me the answer?
D, sir.
No, it is not right. The correct answer will be A. Okay, I will tell you
Uh-huh.
why. Okay, if you see this circle that I have drawn earlier, so here we should not say that it is like pure tension. This stress block is still a very small distance above the y-axis. Okay, at from the base, so there is some small shear force that is present in this. That's why if you see in the circle that I have drawn, this is there is an element of shear that is coming into the picture. However, if this point is exactly on the surface, what will happen? There is no shear. There is only flexure. So what will happen? This element is not there. So if this element is not there, what will happen? These 2 points, they will converge and they will appear as a dot somewhere here. Okay, so it will be like this is my axis and this is my dot and this is my circle. Okay, principal stress is this point only because there is no shear acting, so there can be no point above this, no point below this. Okay, so this diagram that was shown in the slide, it should be for a very small shear. So this is a very magnified image of the point that we can see, and this value, it will be very small, very very close to zero. Okay, if it is uh, near the end. Okay, but if it is exactly zero, then it will appear as a point. Got my point, like what I'm trying to say?
Actually, there is a network problem here at my side. I stuck video every time. I left and right. Okay, but you are edible, very good. But
i
my
am
video is stuck.
I am actually recording the session, so if you're facing any problem like in your side, you can always listen back later on.
Okay, okay, sir. I will.
Yeah. So whenever there is connection, just try. You can ask any doubt if you have. Okay. Question number 8. The first diagonal shear crack in the RC beam forms when. So this is a repeat question that we discussed a few slides ago. Now try to answer it again after your understanding about Mohr circle. Okay, so for this question, the correct answer will be B. Okay, so we saw a few slides ago. We say that at a particular point, the maximum stress is the principal stress, and when this principal stress exceeds the tensile strength of concrete, then the cracking starts. Okay, so the direction of crack, the first diagonal shear crack, it forms when the principal tensile strength it exceeds the tensile strength of concrete. Okay. Question number 9. In Mohr circle for a beam subjected to both shear plus flexure, the tensile strength of concrete is considered exceeded when? So when we consider the tensile strength of concrete has exceeded, I am discussing question number 9 right now. In the Mohr circle for a beam subjected to shear plus flexure, when the tensile strength is considered to be exceeded, the stress is exceeded the tensile strength of concrete. Okay, so for this question, the correct answer will be C. How? So suppose this is my Mohr circle that I have drawn. Okay, now this is my shear, this is my flexure, and I know this is my tensile strength of concrete. Okay, and this is the value for tensile strength. So when the radius of my circle, it passes the uh, when my circle touches this tensile strength line, then we can say that the uh, tensile strength of concrete has been exceeded at a particular section. Okay, so this is my circle which is representing the stress at a particular cross section. Okay, if this stress is exceeding the tensile strength of concrete, then we can say that the Mohr circle will also cross the line. Okay, so that's why the correct answer is B. Okay, any doubt in this part? Yeah, the correct answer is B. Okay, you can unmute and speak also so that the conversation is proper, or I will see the chat box, no issue. Okay, now let's move ahead. So how we provide resistance against shear cracking is our next discussion. Now here, unlike flexure where only steel reinforcements are assumed to provide resistance to bending, in shear both concrete and steel contribute to the shear strength of a reinforced concrete member. So first we'll see how concrete contributes, and then we'll see how we design for shear reinforcement. Okay, so concrete, it resists the diagonal shear crack in three ways. Okay, first with the help of the uncracked concrete portion on the compression side, which is yet to crack. Okay, second, due to the aggregate interlocking, okay, which delays the growth of shear crack through them. So if we see aggregate, the crack is growing. Now this crack needs to make its way across the aggregate. It can't go directly through the aggregate. So that's why we say this aggregate interlocking, it delays the shear crack growth. Okay, by not allowing crack to grow through them. Instead, it needs to create a path across the aggregate. Okay, so in this way aggregate interlocking also contributes in resisting shear. And third is due to dowel action of longitudinal rebar, which also resists the propagation of shear crack to them. Okay, so this reinforcement which are present, it will also provide some resistance to shear crack from growing across it. Okay, so that's why in IS 456, when we calculate shear strength of concrete, we say it is a summation of all these three contribution: the compression zone, the uncracked concrete in the compression zone, the aggregate interlocking, and the dowel action. Okay, and that's why when we consider the shear strength of concrete as per table 19 of IS 456, we need two information: the percentage reinforcement area to take into consider the dowel action of reinforcement bar, and the concrete grade to take into consideration this uncracked concrete and aggregate interlocking. Okay, so that's why both of those parameters that are needed to determine the shear strength of concrete. In addition to concrete shear strength, we provide shear reinforcement in reinforced concrete to resist shear force. Now, there can be different ways in which shear reinforcements can be provided. Okay, first is by providing vertical stirrups. Okay, so if you see vertical stirrups, it can be one-legged stirrup, two-leg stirrups, four-leg stirrup, and six-leg stirrups. So these steel bars, they are vertically placed along the tension reinforcement at different spacing along the length of the beam to provide the resistance. So this is a cross-sectional view. Okay, so there are reinforcement on the compression side, there is reinforcement on the tension side, and across these reinforcement, okay, this is B, this is D, this is a cross-sectional view. You can see this is the shear stirrups. Okay, vertical stirrups. Okay, then there can be bend up bars. Okay, so these are longitudinal bar which can be bent near the support where it is not required to resist the bending moment. So we saw when we talk about flange section that near the support we need moment, there is negative moment, and away from the support there is positive moment. So the reinforcement that we are providing near the support on the compression side, they are not required now here in the middle part where the bending is maximum at the bottom. So these bars, they are bended like this. Okay, which to resist shear crack from growing, and these are known as band up bars. Okay, and third is providing inclined stirrups. So generally these stirrups, they are provided at an angle of 45-degree to resist the crack from growing through them. So we'll see the design of this vertical stirrups and inclined stirrups in our discussion ahead. Now we know in reinforced concrete, both steel and concrete, they resist shear. So for a beam having a uniform depth, we determine the nominal shear stress is given by this equation. So if we know the shear force what is acting on the concrete, we can determine the shear stress acting on the concrete by this formula: tau v is equal to vu upon bd, where we use the shear force that is acting on the concrete due to design load, b is the width of the member, and d is the depth, effective depth of the member. Okay, so this is known as nominal shear stress that we need to resist, that for which we need to design for. Now for determining the shear strength of concrete, we use table number 19. Okay, so before that, how much. Okay, so this table number 19 tells us how much resistance concrete will provide to shear. Okay, so based on the area of steel reinforcement that we have provided, percentage area of longitudinal bars, and the concrete grade, we can determine the shear strength of concrete. So suppose my percentage reinforcement is 1% and my concrete grade is M20, the shear strength of concrete will be 0.62. Okay, if this is the shear strength of concrete, then how much shear strength we need to design, how much shear needs to be resisted by the shear reinforcement, that will be nothing but vus is equal to vu upon minus vc. So v is the total shear force and this is the shear strength of concrete. So subtracting this will give us the amount of shear that we need steel reinforcement to resist, shear reinforcements to resist. Okay, then there is one more factor which is known as maximum shear strength limit, okay, which is determined by this table 20 of IS 456. So in no case the nominal shear stress that we derived, tau v, it can be greater than the maximum shear strength limit. If this happens, then we need to redesign the section by either increasing b or d or both, so that we can reduce tau v. So we now know tau v is equal to vu upon bd. Okay, now if my tau v is more than tau c max, then we need to redesign the section. So for that, what we can do, we can either increase b or we can increase d or we can increase both. If we will increase this, then tau will reduce and it may come lower than tau c max. And from table 20, for different grades of concrete, we have different values of tau c max that is given to us. Okay, so if tau v is less than tau c max, we are redesigning the section. If tau v is less than tau c max and it is more than tau c, then it means that concrete is not enough to resist the shear. So we provide shear reinforcement also. And if the shear force that is acting, it is less than the shear strength of concrete, then we don't need shear reinforcement at all. So we provide a nominal reinforcement, a minimum value of shear reinforcement we still need to provide, which is known as nominal reinforcement. Okay, so how to design for shear reinforcement? Design of stirrups means two things. First is the area. What is the area of stirrups we want, and what at what spacing we want to place the stirrups. So these are like rectangular cages. Okay, so if you see this cross section, so this will be like cage here, then cage here, then cage here along the length of my beam. So this area of one cage, that is ASV, and the distance between these two cages we denote by SV. Okay, so both of these things we need to determine. Now the area of stirrup we can determine from the this configuration, whether it is a single legged or a double legged, an area of each leg, like what diameter reinforcement we are using, 8 mm, 10 mm, 12 mm, whatever we are using, and spacing we determine by a relationship. Okay, in no case spacing should exceed 0.75 times d, or in inclined syrup it can't exceed d, and in no case it should exceed the value of 300 mm. So whatever SV we determine, we check with these two values. Okay, if it is lower than these two value, it is okay. If it is higher, then we need to provide the these values. Suppose my d is 400. Okay, then my 0.75d, it will come out to be 300. Okay, and the spacing that I have calculated, it is coming out to be 350. So we don't need to provide 350 mm spacing, we need to provide 300 mm spacing. Okay, so that is what this clause says. Okay, now how we determine spacing? So we know the amount of shear that the stirrups needs to resist. So it is tau v minus tau c. Okay, times BD will give me the shear stress that the stirrups wants to resist, needs to resist. And at a particular section, uh, the shear stress, we can write it is equal to 0.87 Fy ASV D upon SV. So this D upon SV will give me the number of the stirrups that are there in a particular section. Now from this, we can estimate ASV upon SV. If we rearrange, we can write like this, and if we know the ASV value, we can determine the SV value. Okay, the spacing between the stirrups. Okay, for nominal reinforcement, where I don't need any kind of shear reinforcement, concrete is enough to resist the shear. We use this relationship that is given by IS code. Okay, so fixing the ASV, we know B, we know Fy, we determine the nominal shear spacing, stirrup spacing. Okay, so this is the approach of design of a shear reinforcement and shear reinforcement for a concrete section. Let's see one numerical just to understand the application of this approach. Okay, so this is the numerical. I will give you a couple of minutes to just read the numerical, and then I will tell you the solution. In the meantime, if you have any doubt regarding this design approach of shear reinforcement, you can ask. Okay, just give this question a try. What all you need to know? You need to calculate tau v, you need to calculate tau c, you need to calculate tau c max, and then compare in which case you are belonging, and then tell me whether I need to provide shear reinforcement, or I need to redesign the section, or I need to provide nominal reinforcement. That part you can just do very quickly before I tell you the solution. Just give it a try. Okay, let's see the solution. Okay, so tau v, it will be equal to shear force 40 kilonewton, 40 into 1000 divided by b times d. So b is 300 and effective depth is 500. Okay, so when you will solve, it will come out to be 0.27 MPa. Okay, now tau c max for a M20 grade concrete, it is equal to 2.8 MPa. Okay, so since my tau v is less than tau c max, then we don't need to redesign the section. Okay, the section is safe. Now for tau c, the shear strength of concrete, we first need to determine the percentage reinforcement, longitudinal reinforcement, that is P. So P is given by 100 times AST divided by B times D. So it will come out to be 100 into AST. It is given to us, we have provided three number of 20 diameter bars. So 3 into 3.14 into 10 into 10. Okay, this is my AST upon B into D, 300 into 500. Okay, so when you will solve the percentage reinforcement, it will come out to be 0.628%. Okay, so for this we need to go to the table. Okay, how we'll use the table? By using interpolation. Okay, so we know in this table for 0.5% the shear strength is 0.48, and for 0.75% the shear strength is 0.56, and our value is lying between these two values, 0.57, 0.5 and 0.75. So we'll do a basic interpolation of value. Okay, so what we do in such cases, we use this equation. We know the 2 points and we want to find the value at a middle point, so we'll assume this is a straight line. Okay, so like this. So I will assume this is a straight line. I know the dimension of these 2 points, xy coordinate. I know the xy coordinate of these 2 points. So I will write the equation of this line and I will find the y coordinate if I know the x coordinate of any point in between. Okay. So upon doing that interpolation, you will find that tau c will come out to be 0.52 MPa. Okay. Now you see tau v is less than tau c. Okay, so my tau v, the shear strength that I want my reinforced concrete to resist, it is less than the shear strength of, this is shear stress. Okay, the shear stress that is acting on my reinforced concrete, it is less than the shear strength of concrete. Okay, so this means that my concrete is enough to resist the shear. So we'll provide nominal reinforcement. Okay, and for nominal reinforcement, we saw what is the formula. This is the formula. Okay, I will just copy this formula. Okay, this is the formula for nominal reinforcement. Now ASV, let's assume we are providing 8 diameter two-legged stirrups, okay, of FE 415 grade. Okay, so ASV for this will be number of legs 2 times pi r square, 3.14 into 4 into 4, so it will come out to be 100.48 square. Okay, we know SV, so we can estimate SV. So this I will substitute as 100.48. D I know is equal to 300.487. Fy is 415. Okay, so when you will solve this, your SV value, it will come out to be, SV should be less than or equal to 302.32 Now we saw earlier condition, there are two checks for minimum spacing. One is 0.75 times D and one is 300 So my 0.75 times D, it will come out to be 0.75 times 500, which will be equal to 337.5. 0.75 times 500, yes. Okay, it will come out to be 350. Okay, and 300. Now since my 302 is more than 300, then we need to provide a spacing of 300 and not 302 Okay, so I will provide this 8 dia two leg stirrups at a distance of 300 center to center across the length of my reinforcement, and this is how shear redesign is done. Any doubt in this question? How we use different tables of IS 456 and how we decided on the spacing, and how we use the minimum spacing clause of IS 456. Any doubts in this part?
No, sir, no, sir. Thank you.
Okay, so let's move ahead now. Now there is one more important point to remember here. What that is, what is the critical section for shear design, from where the chances of shear stress is the maximum. So IS 456 code says that when we have a simply support, when we have a column and a beam which is under uniformly distributed load, then this critical section, it lies at a distance d away from the support. So when you are doing the shear force diagram, okay, so at a distance d away from the support, you can see what is the shear force acting, and for this shear force, you can design the shear reinforcement for the entire section. Okay, for such cases where there is beam column joint, okay, and there is uniform loading on one side, then this critical section is at a distance d away from the joint. However, if there is very heavy loading acting, heavy point load acting at a point, then this critical section can be anywhere between two times the depth of effective depth of the section. Okay. And for cases where we have this end section, L type of section, the critical section, it lies at this face only. Okay, so when you draw the shear force diagram, whatever shear force is acting at along this axis, it is taken as critical shear, and for this shear we need to design. Okay, so you saw an application of this concept in the recorded session. So this was the beam, okay, which was under uniformly distributed load. For this uniformly distributed load, we can make the shear force diagram. So this was the shear force diagram that we made. Okay, now we saw at a distance d away from the support, we know the shear force is the critical. So this distance we took 640 was the value of d. So for this d, we estimated what will be the shear force. Okay, from the shear force diagram, we know this is straight line and this value is 342. So based on the slope of this line, we can calculate what will be the value at a distance d. Okay, now for this distance d, we design the, so this is my VU. Okay, for this I will calculate tau V and I will design the shear reinforcement. However, we see that as we go away from the support, the shear force decreases. So we can even do detailing in different steps. Okay, so for this section here, I can design based on this value of 265. Now there will be a point when my shear stress tau V will become equal to tau C. Okay, so for those section we can design differently where the gaps between the reinforcement, the stirrups will be more. And if my tau V is less than tau C, that may come very near to the center, then we can design it as a different zone. So that's how there were different zones that were decided: zone A, zone B, zone C, and zone D. Okay, zone A, B, C, and D. Okay, in these zones, what is the difference? The stirrups are the same. It is two-legged 8 mm dia stirrups. However, the spacing is changing. For zone C and zone D, the spacing was 150 mm center to center. But for zone A and zone B, the spacing was increased to 300 mm center to center, because here the shear is acting very small. Okay, shear force is very small. So we can increase the spacing also, which will optimize our design and reduce the cost. Okay. Now, what if my depth of the beam is not the same, it is changing? So in such cases, there is two possibility: either the depth of the beam is increasing in the direction of shear force increment. So suppose this is my beam and my shear force is increasing like this, okay, from the support, and in the same direction my depth of the beam is also increasing. So as you can see in this diagram, okay, the bending moment diagram, okay, and the shear force diagram. So shear force is increasing in the direction of depth of the beam increase. Okay, so in such sorry, in the direction where bending moment is increasing, in the same direction the depth of beam is also increasing. Okay, so for such cases, how we determine the net shear force? So at this particular location, I know mu value, what is the bending moment acting, and I know this force times the lever arm distance is equal to the bending moment. So I can write force is equal to bending moment upon lever arm distance z. And since we know that this neutral axis depth, it is very close to the top, then we assume that z is almost equal to d. So we write tau, this compression force and tension force, it is almost equal to mu by d. Okay, now this force is acting like this at this point, and if we know at what rate this depth of beam is changing at an angle b, so we can deconvolute this force into two components: horizontal component and vertical component. So this total shear vu, it should be resisted by this vu net plus tu times 10 beta. Okay, so this vu net that we want for the shear resistance that we want, it will be nothing but vu minus tu 10 beta, and tu is nothing but mu by d. Okay, so this is the equation that we write for shear. Similarly, if my shear force, if the depth of the beam is decreasing in the direction where mu is increasing, then this minus will become plus. Okay, because now 10 beta will act on the opposite side, on the opposite side. This, now this will be vu 10 beta. Okay, so vu minus plus tu 10 beta will be equal to vu net, and tu I can write as mu by d, so we get this formula. Okay. Additionally, if we are providing inclined stirrups, then we need to make certain changes in the calculation. So one inclined stirrup, it can only develop shear equal to the tensile capacity projected along the crack. Okay, so you see what is the spacing between two cracks. So along this crack, we know how much stirrups they are contributing. So suppose this angle is beta. Okay, this angle is alpha, and this angle at which crack is propagating is beta. So this total length, the spacing between two crack, the next crack is coming here. Okay, so the spacing between two crack, we can write this is the distance d. So this d minus d dash is like this is the complete distance d, and this is d dash. Okay, so this is like the cover for the shear reinforcement at the top, which is d dash. So this is d minus d dash times. Okay, so the length I know. So based on trigonometry, I can calculate this length and this length. So it will come out to be d minus d dash times cot alpha plus cot beta. Okay, so effective number of bars in this region will be this length upon spacing between the bars, so this spacing sv. Okay, so this will give me the effective number of bar which is resisting one crack. Okay, now maximum shear carried by one stirrup, we can write it as asv times 0.87 fy times sine alpha. Okay, so total shear carried by n number of stirrups we can write by this formula. Okay, how this we came to this formula? By assuming beta is equal to 45. Okay, because we know shear crack, they propagate at an angle very close to 45 degree. So cot beta will become equal to 1. Cot alpha will write as cos alpha upon sine alpha. Okay, so this will be cos alpha plus sine alpha upon sine alpha. So when you will substitute these relationships here, you will find sine alpha and sine alpha, it will cancel out, and you will get total shear carried by an n stirrups will be asv times 0.87 fy times cos alpha plus sine alpha into dc. So this dc is this d minus d dash upon sv. Okay, so n times this value is what we have denoted here, and this is given in clause 40.4 of is 456. Okay, so this is how we determine the shear carried by inclined stirrups. Okay, so let's see one numerical where we are combining both these things. Okay, where we have inclined stirrups also, and we have changing varying depth of section also. Okay, so in this question we have a simply supported RC beam which has a span of 6 meter and a web width of 250 mm. Okay, the effective depth d, it is varying linearly in the first 3 meter from the left of the support as 550 to 350 mm. So it is decreasing along the span, and it is subjected to a uniformly distributed load of 80 kilonewton per meter. Okay, which has included self weight also. We need to consider concrete is 30 M30 grade and steel reinforcement is M500 grade, and you need to provide two leg 10 stirrups at an inclination of 600 mm, 60 degree. Okay, so this is like this beam is like this and this. Okay, so here D is 550, and here D is reducing to 350, and after 350 it is constant 350, and this total length is 6 meter, and this length is 3 meter. Okay, and it is subjected to UDL, and we need to provide inclined stirrups. Okay, so suppose this is my section. Okay, so I need to provide inclined stirrups in this. Okay, so we need to design for that. How we'll design? I will pause myself for a couple of minutes, just give it a thought. Okay, how you will do the calculation and how you will start with the problem. So can anyone tell me how I will approach? Can anyone tell me how we will approach this question? Any idea? Okay, so let's see the solution so that you can get a clarity. So first of all, I need to estimate what is the slope. Okay, this angle beta. Okay, so what do we say? What is the slope? So slope will be nothing but the change in the depth, which is so slope will be given by tan beta. Okay, so that is nothing but the change in the depth 550 minus 350 and the length over which this depth is changing, so that is 3 meter, so that will be 3000. So when you will solve this, your angle beta, it will come out to be 3.8 degree. So at 3.8 degree the slope is happening. Okay, so this depth is decreasing at an angle of 3.8 degree. Okay, now as per IS 456, we need to design shear for the shear force corresponding to a distance d from the support. Okay, so how I will determine shear force? So we know it is a uniformly distributed load. Okay, so this is my beam. Okay, so it is uniformly distributed load. Okay, so this load is, I will denote this load as WU. Okay, so and the total length is L. Okay, so total load that I need to resist is WU times L. So the shear, the forces that will act here, it will be WU L by 2 and WU L by 2. Okay, so at a distance d from the support, what is happening? What will be my shear force diagram? So my shear force diagram will be something like this. Okay, here it is WL by 2, it is changing like this, somewhere in between it will be 0, and then it will be maximum like this here. And my bending moment diagram, it will be like this. Okay, so at a distance d from the support, I will estimate this bending moment also, and I will estimate the shear force also. Okay, so first of all, we need to know what is the depth of my section at a distance d from the support. So that we can calculate simply by using the equation of this line. Okay, okay. So my depth d at a distance x is equal to d. It will be nothing but 550 minus the slope, which is 550 minus 350 upon 3000 times x, which is 550. Okay, so when you will do this calculation, the d value, it will come out to be 513 mm. Okay, now for this d value, the for at this distance d, my vu, it will come out to be wu times l, w times l minus WL by 2, sorry, WL by 2, which is the force acting at the support, minus W times X. Okay, this X is this D that I have calculated. Okay, this distance, okay, which is 550 mm. Okay, so when you will do this, it will be W. times L by 2, it will come out to be 240 minus W is 80 times the distance, which is 0.55. So 550 mm I have converted into meter. Okay, so this VU value, it will come out to 196 kilonewton. And similarly, MU value, it will be reaction force at the end A, so times x by 2. Okay, so due to this force, what will be the reaction that will be generated? So it will be 240 into 0.55 minus the reaction force of this UDL up till this distance L. So that is given by WU x square by 2. So that will be 80 times 0.55 times 0.55 by 2. So upon calculation, it will come out to be 119.9 kilonewton meter. Okay, so we know VU, we know MU, we know the slope, and we know the distance. Okay, so what we'll do ahead? So next is we will design. So since uh, how I will estimate the VU net? Okay, so here, since the depth is reducing in the direction of shear, then we need to use the minus case. Okay, so this is the case. Okay, so depth is reducing in the direction of shear, so we'll use the plus case. Okay, so for that, I will estimate VU net. Okay, so VU net I will estimate, and it will, you will see, it will come out to be something 180.4 kilonewton mm by using this formula. Okay, we have all the values. Okay, where is the question? Okay, we have all the values here in this question. Okay, we know VU, we know MU, we know D, and we know 10 beta. So substituting all this value, you will get VU net will be equal to 180.4 kilonewton. Okay, now for this VU net, we need to design for inclined stirrups. So for inclined stirrups, we'll use this formula, total shear. Okay, so this formula, it will be equal to this formula. So ASV we have already fixed, it is given to us, it is 2 into pi into 5 into 5. Okay, so 2 legged stirrups. For this ASV we know. Okay, FY we know, it is 500. Cos alpha and cos beta we know cos 60 and sin 60 value we can calculate. Okay, DC, that is equal to the D. So this D is given to us, it is the depth, effective depth only. So that is given to, it is 513 at the section we have calculated. So we can estimate the SV value simply by solving this equation. Okay, so upon solving, you will find SV will come out to be equal to 266 mm. Okay, which is less than 300 and which is less than D also. So we saw for inclined stirrup, the formula becomes 0.75D. Instead of 0.75D, we need to use D. So D is equal to 513 and 300 mm. Though those two conditions are there, and since 266 is less than both of them, then we can go along with this value. Okay. So from this VU net, you can also solve, like you can also deduct the concrete stress also first. Okay, so if you will do that, this value will reduce. Okay, and if this value suppose reduces to 100 or 90, then you can again see what is the SV. If it is more than 300, then you can reduce. Okay, I did this calculation without deducting the concrete shear strength. Okay, that you can just check once. Okay, that reduction you can do if you want. Okay, so this is how we approach. Basically, I wanted to tell you how we approach the question. We'll first determine the angle at which the decrease is happening. Then we'll determine the distance d from the support at which we need to find the shear force and the bending moment. We will find shear force and the bending moment. Once we find the shear force and the bending moment, we'll estimate the net shear that we want to resist based on whether the depth is increasing or decreasing in the direction of uh, in the direction of a span. Okay, if it is decreasing, we'll use the negative formula. If it is decreasing, we'll use the positive formula. If it is increasing, we use the negative formula. We get the vu net. Once we get the vu net, we'll use this relationship for inclined stirrups, where alpha is already known to us and everything else is known, so we can calculate the sv. Okay, so this is how we approach. Any doubt in this? Is this inclined stirrup part and the uh, uh, different depth of section part clear? Is there any doubt in this section? Okay, now we will start discussing about torsion. So first of all, what is torsion? So torsion is basically a moment that is acting along the longitudinal axis of a reinforced concrete member, which causes twisting action or torque or a torsional movement. Okay, so as you can see in the figure, along the axis of the beam, a moment is applied. Okay, which is causing twisting in the beam cross section. So at any cross section part, if you see how the stress is distributed, so this is normal stress that we calculate from my by I. Okay, and this is torsional stress, so they appear like this. Okay, so at the middle it is 0, at the end it is 0, and somewhere in the mid it is maximum. Okay, so it is a arch like distribution. Okay, how we get this we'll see later on in ahead discussion. Okay, so this is known as torsion. Okay, now how torsion causes failure. So you can see in the first image where you can see this stresses, they are cracking the concrete on the surface like this, and the complete section is getting twisted. Okay, so torsional failure of a beam which is showing significant spalling of concrete cover due to twisting action that has been generated here. And in case of columns where we have a long slender column, so as the torsional moment increases, so you see earlier when there was no torsion, the failure was at the base. Okay, but as the torsion moment increases, you can see the failure happens across the cross section due to the twisting action. Okay, now the way stresses are generated due to torsion, they can vary based on the dimension of a reinforced concrete member. So in case of a excess symmetric member like a circular RC member, the section just rotates about the vertical line. Okay, so you see the vertical lines, they are the same, however this horizontal lines, they are getting rotated. So we can say that there is no warping or distortion happening in this section. Warping means warping means out of plane displacement of a cross section along the axis of the torsion. And so here, since the cross section is just rotating, there is no out of plane movement, there is no shape change, we say there is no warping that is happening. And distortion means change in the shape of the cross section. Since there is no shape change happening, then we say there is no distortion, that is also there is no distortion in the member, the section is just rotating. Okay, however, for a non-axis symmetric cross section like a rectangular RC section, this section, when it is deforming under tension, it is changing the shape also, and thus there is both warping and distortion that exist in those section. Okay, so for such section, for circular section, you'll see that the maximum torsion, it is present near the surface, at the surface. Okay, for a rectangular section, the stresses are maximum torsion, it exists near the surface, and at surface it again becomes zero. Okay, how this is done we'll see ahead when we'll talk about maximum stress. Okay, now, there can be two ways in which torsion might be produced in a reinforced concrete member. What are these two torsions called? One is called as equilibrium torsion and another is called as compatibility torsion. So, what is equilibrium torsion? Suppose this is my RC section. Okay, so in this torsion is produced due to eccentric loading. So, suppose I am loading providing some load here. Okay, so due to this load there will be some bending moment that will be generated in this beam. So this beam will be subjected to torsion due to the eccentric loading, so that is known as equilibrium torsion, like this shown here. This P will generate some bending moment here that will cause torsion in this member. So this is known as equilibrium torsion. And compatibility torsion, it is the torsion that is induced by the need of a member to undergo an angle of twist to maintain deformation compatibility. So suppose this is my beam, okay, which is loaded by load P. Now due to this P load there will be some moment that will be generated here, and this moment M will become a torsional twisting moment for this element here. Okay, so this element, it will try to rotate to maintain the equilibrium, to maintain the compatibility of this whole structure, and this such torsion is, it is known as compatibility torsion. Now the amount of twisting that will happen in this member, it will depend upon the torsional stiffness of the member. What is the stiffness against torsion this member is providing? Okay, how we determine the torsional stiffness? Okay, so for this we use this linear elastic analysis. Okay, the torsional stiffness kt, it is given by this equation g times c times upon l, g into c upon l. So g is taken as zero point 0.4 times moe of the concrete, and c is taken as 0.5 k, for which again there is a relationship that has been provided. Okay, so from these relationships we can calculate what is the torsional stiffness of a member, and this higher is the stiffness, lower will be the twisting that will happen in this member. Okay, so that is what torsional stiffness means. Now, in the first slide of torsion, we saw torsional stress distribution. So, how we determine the torsional stress distribution at a particular location, and thus how can we determine the maximum torsional stress? For this, we have two theories, among which the first one is known as soap film analogy. Okay, what this theory says, so it is a theory which helps us to visualize the general stress distribution at an arbitrary section. So this theory was proposed by a scientist named Prandtl. Okay, so he says that if we take a thin wire and bend it in a cross section shape of a bar and dip in a soap solution, the soap film that forms inside the loop, it assumes the surface with minimum potential energy. So suppose this is a wire that I've bent in a circular cross section, and if I dip this cross sectional wire in a soap bath, and I raise this, so I will see that the soap bubble will find this curvature on the surface. So this curvature is the surface is represents the minimum potential energy, and this deflected profile of the soap fin, it represents the torsional stress distribution on this curvature on this section, and the slope at any points will correspond to the shear stress direction and intensity at that point at a particular section, and torsional rigidity will be proportional to the volume of the surface. So at any point if I draw the tangent, it will give me the intensity of shear stress, and the total rigidity of this section, it will be denoted by the volume enclosed by this soap bubble. Okay, so this is known as soap film analogy. So here, if we take the soap film analogy for a circular section, so in the circular section, the soap, this film will take a shape of a dome. Okay, so this kind of dome you will see it will form. Okay, so shear stress, we say it will vary linearly with the radius, and it is given by this relationship. Tau is equal to T times R upon J, where T is the applied torque, R is the distance from the center, and J is the moment of inertia. Okay, and maximum torque, then we can say when R is maximum. So when R will be maximum, when we are talking about the outer radius R. Okay, so that's why we say for a circular section, the torsion is maximum at the surface. Okay, however, for a rectangular section, we'll see the soap film, it won't be as symmetric as it was there for a circular section. It has a sharp bend near the corner and it will become zero again. Okay, so the shear stress in such cases, it is denoted by this formula. Okay, maximum shear, it is given by T upon alpha times x square y, where x and y is this dimensional property which is given by the shape factor. Okay, and shape factor alpha is given by this relationship. Okay, So x and y are the section dimension. This may be x, this may be y, and from the x and y we calculate the aspect ratio, shape factor, and we determine the maximum shear. Okay, so both of these formulas that you see here, these was derived by the force-of-will analogy by Prandtl to relate how the torsional stress it distributes for a circular section and for a rectangular section. Okay, now second theory for determining maximum torsion, it is known as thin wall tube theory. Okay, or we can say shear flow concept. So in this we consider we have a hollow thin section cross section like circular cross section, rectangular tube, or a box girder. Okay, and this tube is subjected to some torsional force T along the longitudinal axis. So you can see there is an arbitrary shape, and this is subjected to a torsion about its longitudinal axis. So if we take a small cross section ABCD on its surface, then this cross section it will carry some torque, shear stress tau 1, tau 2, tau 3, and tau 4 across its surface. So since it is in equilibrium, we can say that the shear force that is acting in the horizontal direction will be equal. So this shear force VAB which should be equal to VCD. So this tau 1 times T1 into dx. So dx is basically the length of this section. Okay, it will be equal to tau 2 times T2 times dx. So from this we get this equation tau 1 T1 is equal to tau 2 T2, and this is what is known as shear flow, tau times the thickness of the member. Okay, so for a closed thin wall section we say shear flow is constant along the perimeter. Okay, so for the entire section the shear flow we say it is constant and it is equal to tau times T. So T is the thickness of this tube. Okay, here we are seeing that it is varying. However, if the thickness is increasing, the tau value will decrease. Eventually the tau times T will remain the same. So this is the theory which is known as shear flow concept. Okay, now to connect the shear flow with applied torque, we write this equation. Torque is the sum of force times the lever arm distance. So T is equal to R times Q times ds. Ds is a small element, and Q is the force acting in the small element, and R is the distance from the center. Okay, so for this q we can write q is the shear flow. Okay, so since q is constant, I will take it out of integration. Why I'm doing integration here? So that I can calculate the torque the entire torque on this cross section. Okay, so since q is constant, we have seen from the shear flow concept q remains constant along the perimeter, so that why it was taken out. And this r times ds, it is nothing but equal to 2 times a naught. So if we draw a circle from the midline, okay, then the area enclosed by this thing it is denoted by a naught, and this integration r times ds it is said that it is equal to 2 times a naught. Okay, so we can write t is equal to 2 a naught times q, and since we know what is q is nothing but uh, uh, torque times t, so we can find the tau value. It is equal to t upon 2 a naught in times t. So t is the force that we have exerted, and the stress that is generated in this member can be denoted by this relationship. Okay, so this is what is known as thin wall tube theory. Any doubt in these two theories? So these relationships are basically something. Sir, in column general failure is buckling. How can I understand buckling or torsion? See, torsion is something that is creating twisting movement. Buckling is something that is creating bending. Okay, so if you see on this slide again, you could have unmuted and spoken at that time. Okay, I will just explain you here. Where is my cursor? Okay, so this is my column. Okay, when it is buckling, what happens? It is bending like this. Okay, so we will see deflection that is happening. However, when there is torque, there is twisting that is happening along this. So that's why you see cracking is happening all along the cross section of the member. Okay, the surface falling, the concrete falling is happening. However, if buckling was happening, it would have bended like this. Okay, got the point? Buckling will lead to bending. Torsion is leading to cracking of the cover concrete due to twisting. So based on the deformation profile of the column, you can judge whether torsion is dominating or buckling is dominating. Okay, try to answer these these three questions. So this is based on this soap film theory and Prandel's soap film analogy and thin wall tube theory. So first question says, in the reinforced concrete, torsion is generally considered together with. So when we talk about reinforced concrete, what all things we take into account with along with torsion? Can you tell me the answer? Okay, okay, no problem. You can type in the chat box. Yeah, the correct answer will be shear and bending. So you will see when we'll talk about design as per IS 456, you'll see what how we are taking torsion into account. We are adding an element in the net shear force and in the net bending moment. Okay, and for that net shear force and net bending moment, we'll design the reinforced concrete that will be safe for shear also, safe for bending also, and safe for torsion also. In Prandel's soap-fill analogy for torsion, which of the following points are true? Can anyone tell me the answer?
A, sir.
Okay. What is the problem with B? Is B incorrect? So when I showed you what Prandel's theory says, so he said 2 points. The slope at the surface, it represents the shear stress intensity and direction, and the volume enclosed by this soap bubble, it represents the torsional rigidity. So if you see this slide initially, okay, the slope, the torsional rigidity, it is proportional to the volume of the soap film. Okay, so that's why the answer will be both A and B. Sorry. Got my point?
Yes, sir. Yes,
So
sir.
this is the basis of his theory, like something that he came up with. Okay, the slope and the volume. Okay, the analogy that he built up. Okay. Now in thin wall tube theory, under torsion, the shear force is, which point is correct for shear flow? Not shear force, shear flow. So shear flow was equal to torque, torsional force times the thickness of the member. So what will be the correct answer? The correct answer will be B. Okay, so we saw shear flow is constant across the element. Okay, if you go 2 slides back, so we derived this equation. Okay, at any section, tau 1 times T1 is equal to tau 2 times T2. So we say shear flow Q is equal to tau times T, and for a closed thin walled cross section, the shear flow is constant along the perimeter. Okay, even if thickness changes, it will remain constant. Okay, so that's why the correct answer will be B. Got it? Okay. So I have three numericals here, very small numericals that I won't discuss with you right now, but I will just keep it here so that you can solve on your own. Okay. So these are very simple numericals where you need to use the formulas that we have seen. So in the first question, circular shaft torque is given maximum shear stress. So how you will calculate maximum shear stress using this formula. So you know T value is given to you, R is given to you, J you can calculate, that is pi d cube, pi d to the power 4 by 32. So from that you will get the maximum shear stress tau. Okay. Second question, rectangular section is given. Then you need to calculate maximum shear stress. So you need to use this second formula that we saw. Maximum shear stress is equal to T upon alpha times x square y. So x and y is given to you for rectangular section. Alpha you can estimate from this equation and you can estimate the maximum shear stress. Okay. And in the third question, this thin wall tube theory, dimension is given to you, thickness is given to you. Okay. So for this, you can estimate A naught. A naught is nothing but this dimension minus 5 and dimension minus 5 and the enclosed area by the rectangle, so that will be a naught, and t is given to you. So these are like very simple questions that are related to these three theory. So I will expect you to solve, give it a try on your own. Just solve these three questions on your own. If you are not able to solve, if you are not able to get the value, we'll discuss in the next session. Okay. Why I'm pushing here, because we have a complete section where we need to understand how IS 456 takes into account the torsion design, which is more important to us right now. So that's why I'm skipping this part. But just give it a try, because these questions can be important in terms of assignment and in terms of exam, NPTEL exam if you're giving. So this will be very simple question that if you won't know how to solve, will eventually be a loss for you, okay, in exam. Okay, just give it a try on your own. Okay, can I move ahead?
Yes, sir. Yes, sir.
Okay, just but give it a try so that you're clear with the application. Okay, now
Okay,
how
sir.
cracking in concrete, reinforced concrete section appears due to torsional movement. So we saw there is uh, surface cracking that appears. Okay, so how this occurs, so for that there is a theory which is known as skew banding theory. So what this theory says, so in a reinforced concrete beam that is subjected to torsion, the internal stresses are not just pure torsional shear, but in reality the principal tensile stresses are produced at an angle of inclination which is known as q angle along the longitudinal axis. So what they say, when we are applying a torque T. Okay, so the torsional stresses that are produced, these are not the principal stresses. However, principal stresses will be produced at some angle of inclination, and that's why we say that is known as Q bending. Okay, so along this inclination angle, the cracking will propagate. So that's why you see under pure torsion, the cracking is like this. Okay, at some inclination. Okay, hence the torsional crack, they are observed to occur at an inclination rather than as parallel to the face. Okay, so the same concept that we used for shear, where the cracking is propagating diagonally, the same concept applies here. Along the principal stress orientation, the cracking will propagate. Okay, and that's why, since the cracking is propagating at an angle, at a skew angle, okay, it is known as skew bending theory. However, when there's both torsion and shear effect that is happening, so suppose this is my stress distribution due to torsion and this is my stress distribution due to shear. So you'll see on this opposite face, the torsion and shear are acting in opposite direction, so they will cancel each other out and there will be one vertical crack due to flexure that will be there. However, on this face, the torsion and shear are on the same direction. So at this phase, there will be cracking that will propagate along the principal axis. So there will be stress that crack will propagate at an angle. So that's why the crack pattern, it may change. It may look like this. Okay, then again vertical, then again inclined, then again inclined. So this is the crack pattern. Okay, so depending upon the combination of forces, the crack pattern can change. And since there is cracking happening all across the cross section, so IS 45 code says it may be required that we need to provide some side phase reinforcements also. Okay, so some reinforcements on the side, some reinforcements on the top may also be required for us, because now the cracking is not just at the bottom or diagonal, it is happening along the perimeter of the entire cross section. Okay, so we may need uh, uh, reinforcement on the sides, on the top, and then on the bottom, everywhere. Okay, now how to design for this reinforcements for a known torsional moment. So for this we will refer to IS 456, and IS 456 takes this effect based on skew bending theory itself. Okay, so it says that torsion in RC beam, it is resistive if the member in bending is bending upon about an inclined axis with longitudinal reinforcement carrying the tensile force and transverse stirrups carrying the shear force. So what IS 456 code tries to say here, so if we can take this effect of torsional moment and convert it into effective bending moment and effective shear force, then we can account for torsion safely in a reinforced concrete member. Okay, so for that there are different clauses that are present. Okay, so for getting effective longitudinal reinforcement we need to calculate the effective moment. So this effective moment, it is given by me1 is equal to m plus mt, and mt is the torsional moment. Okay, m is the bending moment that is happening due to loading, and mt is the torsional moment that we are applying on the beam. So net moment we calculate, and what is how we estimate this torsional moment if we know the torque. So that is given by this equation, mt is equal to t times 1 plus d by b upon 1.7. So d is the overall depth, b is the width of the member. So from this, knowing the torque, we can calculate the torsional moment, and knowing the torsional moment we can estimate the net bending moment. For this net bending moment we'll design the longitudinal reinforcement as we did for flexure. However, there is one more thing that code says. If this MT value is more than M, then code says that longitudinal reinforcement shall be provided in the flexure part also. Suppose this is my cross section. Okay, if my MT is less than M, then we just need to provide reinforcement on the tension side. Okay. However, if my MT is more than M, then code says along with the reinforcement on the tension side, you need to provide some reinforcement on the compression side also. And how you calculate this? By this equivalent moment. Me2 is equal to MT minus M. Okay, so difference between these two moment, for that moment you need to design the reinforcement on the compression side also. Okay, so this is what code says about reinforcement on tension side and on compression side, where torque effect is also taken into account. Now, for shear, what code says the net shear due to torque, it is given by this equation. So 1.6 T by B is the contribution of torque, and V is the shear force that is already acting in the beam. So we can estimate the equivalent shear. Okay, from this equivalent shear we can get the equivalent shear force. Okay, from shear force we can get the equivalent shear stress. If the shear stress is more than tau c max, then we need to redesign the section. If it is less than tau c, then we need to provide minimum reinforcement by this equation that we have seen earlier. And if it is more than tau c, then we need to provide both longitudinal and transfer reinforcement. Okay, how we design for transfer reinforcement? So for this, code has given this formula. Okay, so two leg closed hoops enclosing the corner longitudinal bar shall be provided with an area of cross section ASV. So we need to provide two legged closed longitudinal. Here we can't use a single legged stirrups. Code says that when torque is acting, then you need to use closed loop stirrups, so that it can completely enclose the reinforced section from the side, which can resist cracks from everywhere. Okay, so for this, this formula is given. ASV is T times SV. T is the torque force that is acting upon B1 D1 times 0.87 Fy. So this B1 is this distance, center to center distance between the end bars, and D1 is center to center distance where, along the end bars here. Okay, plus V times SV. V is the shear force. VU we can write. times SV upon 2.5 D1 times 8.87 Fy. Okay, so this is the formula for area of stirrups. If we know ASV, then we can calculate SV. Okay, so B1 and D1 I have shown you here. It is the center to center distance between corner bars in the direction of width and depth. And this total ASV, it should always be more than this formula. Tau VE minus tau T, tau C times BSV upon 87 Fy. Okay, so it should be more than this. Okay, so using these two relationship, we design for the transverse reinforcement. And what about spacing? So if we get the spacing value, we need to check with these three conditions. So spacing should be less than or equal to these three conditions. X1 is the corner to corner distance, not center to center distance. Okay, so this is like from this corner to this corner. A1 was this to this. Okay, and this to this. Okay, now x1 is corner to corner and corner to corner here, y1. Okay, so these three conditions should satisfy. So whatever SV I'm getting, it should be lower than these three values. If it is more than these values, then I need to take the minimum of these three, and that I need to use as stirrup spacing. Okay, and if my D, this overall depth D, is greater than 450 mm, okay, then code says that we need to provide some side phase reinforcement also, which is equal to 0.1% the web area. So web area is B times D. So 0.1% of this we need to provide on the side, which is equally distributed. So if one bar here, one bar here, if two bars here, two bars here, like that we need to distribute. Okay, and their spacing should be minimum of 300 mm or web thickness. Okay, so these are the clause that has been given by is code for torsional design. Okay, first we saw how we take torsion design into longitudinal reinforcement. Then we saw how torsion is taken into account for transverse reinforcement, and how when we need to provide side phase reinforcement. So just to understand the application of these formulas and this theory, let's solve a numerical. Okay, so I will pause myself for a minute. I will let you think how we will start with this numerical, and then we'll discuss. Other than class, you can use the discussion forum of the course if you have any doubts regarding assignment. Or once I end this session, I will keep make myself available. Then you can clarify your doubts. Okay, other than that, you can try and drop me a mail whenever possible. If I am free and I am able to reply, I will reply you back via mail. But I will say, if you have any doubts, just discuss during the session only, because during the session it is possible. Okay, apart from session it will be very difficult. Okay, at the end of this session I will give you my mail ID. Okay, right now just think about this question, how we'll approach. So can any one of you tell me how you will solve this question? What will be the approach? Okay, so let me solve. Okay, so first I will calculate the torsional moment, how much moment torque is generating. So torsional moment, we saw it is given by this formula. I will just copy the formula. Mt is equal to T times 1 plus B by D. Okay, so in this, when I will substitute the value, it will be 150. Torque is given to us in the question, it is 150 kilonewton meter. Torsion force, it is given to us. This is torsional moment. Okay, how it is converted into bending moment, that is what we are seeing here. So 150 into 1 plus D by B. So total depth is 750 and width is 400 mm. Okay, whole upon 1.7. Okay, so with this MT will come out to be 253.67 kilonewton meter. Okay, so equivalent bending moment it will be nothing but me1 is equal to m plus mt. Okay, so it will be 120, which is given to us in the question. Bending moment is 120 kilonewton meter and shear force is 75. So 120 plus 253.67, so it will be 373.67 kilonewton meter. So for this bending moment, I need to design the longitudinal reinforcement in the tension side. Okay, how we will design? So first step will be, I will check mu limiting. Okay, so for FE415 grade, okay, I will assume cover of 50 mm. Okay, if it is not given in the question, it is given 50 mm cover. So my D value will be 700 mm. So for this, when you will calculate mu limiting, it will come out to be 676.2 kilonewton meter. Okay, since my ME1 is less than mu limiting, then I need to design the, it is a under reinforced section for which I will design. So I will use the relationships that we have seen in the last session. Okay, so I will determine the percentage reinforcement. So there is one relationship that we saw here. PT by 100 is equal to FCK upon 2 times Fy whole into 1 minus square root of 1 minus 4.6 times R1 upon FCK. Okay, so this was one relationship that we saw last time in the last session. Okay, so based on this relationship, when you will solve for the mu value, you will get the percentage longitudinal reinforcement required. It will be 0.0058, and for this AST, it will come out to be 0.0058 times 400 times 700. So it will be 1624 mm square. So this is the amount of reinforcement you need to provide on the tension side. However, if you see here, mt is more than m, so 253.67, it is more than 120. So this means we need to provide reinforcement on the compression side also. So for this, how we'll design? Okay, so for compression reinforcement, we know me2 is given by mt minus m. So it is 253.67 minus 120, which will be equal to 133.67 kilonewton meter. Now, for this again, mu limiting, I know mu limiting will remain the same. It is 676.2 kilonewton meter. So again, for this reinforcement, I will do the design. I will design the longitudinal rebars. Okay, so again, the same formula that you saw here, or you can use lever arm equation, or you can use force equilibrium equations, the things that we have seen in the last session. When you will solve the question, you will get the area in the compression steel. It will come out to be 543.2 mm square. So what this says, that we need to provide this much reinforcement on the tension side and this much reinforcement on the compression side. Okay, for resisting both bending moment and torsional moment. Okay, so this is for longitudinal rebars. Now my D is more than 450 mm. So we have seen code says that we need to provide side face reinforcement also. Okay, so I will design for side face reinforcement. It is equal to AST will be equal to 0.1% of gross area. So zero point 0.1 into 0.01 times 400 times 750. So it will come out to be 300 mm square. Okay, so for this much area of reinforcement I will provide on the side. So up till now, what we have designed, so I will just draw a simple diagram. So this is our cross section. Okay, so we are providing some reinforcement at the bottom. Suppose 20 mm reinforcement. Okay, 20 mm reinforcement, 6 reinforcement I have provided at the bottom. At the top, I have provided, suppose two reinforcement of 20 mm to resist this amount of to get this amount of area, and on the sides I am providing some reinforcement. Okay, so this design we have done. Now we need to enclose this longitudinal reinforcement with the closed stirrups. Okay, which will be my transverse reinforcement. Okay, so this design is pending. Okay, how we design for this now? So for shear, we know the formula. There's some doubt. 300 mm square on one side. Okay. So this is like 300 mm square on each side. 0.1% of gross area on each side we need to provide. Okay. So suppose for 300 mm square I am using 16 mm diameter reinforcement, two rebars. So I need to provide two rebars here and two rebars here on each side. Okay. So this formula here, if I forgot to clarify, side face reinforcement per side. Okay, on each side I need to provide 1.1% of the web area. Got the point? Okay, now for shear, uh, so for shear we know the formula. We need to estimate the net shear by this equation. Okay, V is equal to V plus 1.6 T by B. So it is equal to 75 plus 1.6 times T. It is 150 into 1000. Just to convert kilonewton meter into kilonewton mm, divided by B, which is 400 mm. So this will give me value of 675 kilonewton. Okay, and from this I can calculate tau E is equal to V upon BD. Okay, so it will come out to be 2.411 MPa. Okay, now I will check for M25 grade concrete. Okay, M30 grade concrete, tau C max we can see from the table it is 3.1 MPa. So tau E is less than tau C max, so we need to design for shear. We don't need to redesign the section. And since we know the longitudinal reinforcement that we have provided, okay, and we know the grade of concrete which is M30, I can estimate tau C, the concrete shear strength. So when you will do this, okay, so longitudinal reinforcement means this on the tension side that we are considering. So this reinforcement percentage we know what it is. So this percentage was given by 100 into AST upon B times D. Okay, so whatever AST we provided, so this calculation it will come out to be 0.67. Okay, so for 0.67 and M30 grade, we'll use this chart. Okay, table number 19 that we saw earlier. Okay, so for 0.67, it will use the 0.67 will lie between zero point 0.5 and 0.75, and for M30 grade, the value will be like lying between. Okay, so somewhere near this zero point 0.5 and 0.59, between zero point 0.5 and 0.59 will lie my shear strength of concrete. So when you will do the interpolation, you will find that the shear strength will come out to be 0.54 MPa. Okay, now since the shear strength of concrete is not enough to resist this equivalent shear, then we need to design for shear reinforcement. So what we'll do, we will assume ASV. Okay, let's take 12 diameter two legged stirrups. Okay, so ASV will come out to be 2 into 3.14 into 6 into 6. So that will be give my ASV. Okay, so that will be 226.08 mm square. Now, once I know ASV, I need to determine B1 and D1. So B1 is the center to center distance for the this length reinforcement. Okay, so it is 400 minus cover, effective cover on both the side, 50 minus 50. Okay, so B1 is 300 mm, and similarly D1 is total depth D minus 50 minus 50. Okay, the cover, effective cover. So this is my D1. Now I know B1, I know D1, I know ASV. So what I will do, I will use this relationship. ASV is equal to this one. I'll just copy this. Okay, so this relationship will use. Okay, in this we know ASV is equal to 226.08 into 1000. No, 226.08. T we know is 150 into 10 to the power 6. Okay, SV we need to estimate. B1 D1 we know. B1 is equal to 300. D1 is equal to 650. 0.87 Fy we know it is 415 grade steel. We know is equal to 75 kilonewtons, so 75 into 1000. D1 it is 650.87 Fy it is 415. So upon solving this you will get SV is equal to 100.107 mm. Now we need to check for minimum spacing. So for this we had the three relationships, okay, that we were concerned with. Okay, so I'll just copy this formula. So for minimum spacing, okay, we'll see this. Okay, so x1 is the end to end distance, not the center to center distance. So I will estimate end to end distance. So for this I need to know the reinforcement diameter also. Okay, so like I will draw here. So suppose this is my section. Okay, these are my reinforcement at the top, and these are my reinforcement at the bottom, and these are my side reinforcement. So this is total depth, capital D. Okay, and this is my cover, this is my cover. So subtracting both the cover we got B1 and D1, okay, for both the side. Okay, now x1 and y1 again. Okay, so this is x and this is y. Okay, so if I know this distance is B1, okay, so in B1 if I will add the reinforcement dia of both the side, then I will get x1. Okay, similarly for D1, if I will add reinforcement die of both the side, then I will get Y1. Okay, so suppose I am using 16 mm rebars here and 20 mm rebars here on top and bottom. So what will be my X1? So X1 will be 300 B1 plus 8 plus 8. Okay, half of this diameter on both the side I need to add. So this will be my x1. So it will come out to be 316 mm. Similarly, what will be the will my y1? So here I will write 300 plus 8 plus 8, and y1 will be 650. 650 plus, since I'm using 20 mm, so 10 plus 10. Okay, so this will be my y1. Okay, so divided by 4 it will come out to be around 250 mm. Okay, and this is 300 mm. So since my spacing that I have provided is less than all the three values, then I can go along with the spacing. We can convert this into a whole number of say 100 mm. So what is the transverse reinforcement design? I need to provide two legged of 10 mm diameter reinforcement at a spacing of 100 mm center to center. Okay, and for shear, for longitudinal reinforcement, we designed for the top reinforcement, bottom reinforcement, and the side reinforcement. Okay, so this is how we use all the is clause for designing RC beam, which is subjected to flexure, shear, and torsion combined. 20 by 2, why I did? Because we know the center to center distance. Okay, we know the effective depth. Okay, so center to center distance we know. So we need to add the remaining distance here and here. So that will be radius here and radius here. So that's why I did 10 plus 10. So I know 20 is the diameter, so 10 mm will be the radius. Okay, just don't get confused between B1, D1 and X1, Y1. B1 and D1 is the center to center distance, and X1 and Y1 are the clear distance. Okay. Okay, so this was all about today's session. So we started with A by D ratio concept and Mohr circle. Then we understood shear design as per IS 456, and we saw numerical, and we saw what is the effect of varying depth and varying inclined stirrups. Okay, we talked about torsional behavior of we talked about torsional behavior of reinforced concrete. We had an overview of torsion. We understood how maximum torsion stress can be determined based on soft-fill analogy in thin wall tube theory, and we finally understood how we design for torsion as per IS 456 by modifying bending and shear design. Okay, where torsion is also an element to be considered. Okay, so this was all about today's session. Thank you. Now if you